Hey guys, welcome back. This is now another bed talk that I'll be doing today about section 15.6 about triple integrals. I hope you guys are doing well and staying safe and all that. It's a pretty dreary day here at the moment. It's pretty raining out right now, but we got math in our lives. So let's get to it then. So what I'm going to talk about in this video, overview, is about overview of kind of what triple integrals are. And I'm going to go through a couple different problems, about 3 problems that kind of discuss how to come up with the limits of integration for some of these problems too, and kind of the techniques that we need to think about. We're not going to get into understanding like cylindrical coordinates and spherical coordinates in this section. We're going to talk about this in a little bit, but at least we want to try to get the overview of how do you come up with some of these limit problems? How do you come up with these limits of integration and so on? So the first thing I want to do is think about what these interesting integrals mean. So let's kind of discuss what do I have when I say the integral over f over this region D of f of x, y, dA. What I mean by this here is I'm saying I'm trying to find the net volume of this net volume of this region that is between the xy plane and the f of xy. It could be negative, it could be positive, over my region D. And we have this double integral here because I'm saying that I'm integrating with respect to x and y, for instance, here. Now, what do we mean by a triple integral? For instance, I can integrate something, if I have a function of f of x, y, and z, right? Something like f of x, y, and z here, something like this, I could want to integrate out x, y, and z, for instance. So I could integrate a triple integral, maybe in terms of now this dv here. So we have this thing now. I now have I have 3 variables that I want to integrate out, and I want to integrate that out 3 times. Now you can keep going to this more and more and more. So let's think about a couple of things here. What changed? First thing here is to know that the differentials have changed. The differential here was an area. Now this is a volume. Because what am I doing now? I'm now giving you almost a length, a width, and a height, right? So I need to think about things as dx, dy, dz, a length, and a length. Right now I'm thinking about things over a volume E in this case. Now, what does this function value mean? In this case, this meant the height. But what does it mean here? Well, there's a lot of different physical interpretations that we can think about this. But let's assume I have some region E, something maybe like this water bottle. Maybe this is my region that I'm integrating over this entire thing. Well, what does this really tell me? Well, if I give you a function f of x, y, z, at every single one of these points, I'm basically giving you like the mass of the object, the density of the object. Right? I'm going to tell you basically how much is at every single one of these points. I'm giving you a value everywhere on this, inside the surface, everywhere on that. That's my function f of x, y, z. And this kind of represents in some form, right? I am giving you here more specifically, basically, I'm giving you the density of the object at every single one of these points. And integrating out that will give me a mass, so it will give me the mass of the object. And so that is going to be pretty important for me. I'm giving you the density. You can kind of imagine this thing right here as kind of the density at every point. You know, how dense is the object? It could be all the same. It could be all, you know, different. It could be different depending on what materials you have that you're trying to integrate over. And if I integrate that over 3 times over x, y, and z, I can get the mass of the object. So that's kind of the general interpretation of this. It could be negative. Yes, it's going to be a little bit weird to think about this being negative depending on what f is, but that's if f is positive almost all the time, we kind of start to think about this more as a density. If it's negative, we have to kind of think about a different interpretation. But for right now, let's stick with that. So here what we want to do in this case is to figure out my limits of integration. And sometimes that can be very complicated. And what we're going to do now, this next 3 sections are going to really talk about how do we come up with different limits of integration? How can we figure out different ways to integrate this? So the first thing I want to discuss is in 2 dimensions here, we had 2 things, right? We had a type 1 region and a type 2 region. For instance, a triangle here, if I was to think about just the integral of f of x, y, dA, we had a type 1 region. Type 1 region said I would want to go dy then dx, which meant I want to integrate going upwards first, right? That's my goal. I want to integrate this going upwards. And then I go on my x. I go y and then x. The other way we did it was dx and then dy here, right? I would go across this way, go across horizontally, come up with my lower and upper bounds with respect to y now. X is being bounded by 2 values of y, and go from there. Now, if I have 3 variables, I really have a lot of different options, right? I have, in this case, I only have 2 ways I can do this. Either dy or dx, or dx dy, at least with Cartesian coordinates. If I now have dv being 3 things, dx, dy, and dz here, I'm integrating 3 things. Think about why this works, by the way. I have a length, and a length. The volume here is a length to the third. We're going to need to think about that going forward. Well, I have 3 things. How many different ways can I arrange them? I can arrange them in 6 different ways. I could take with the integral with respect to x, then y, then z. I could do it with respect to x, then z, then y. I could do it with respect to y first. And I have a couple different options there. And then I could do it with respect to z first. And I have 2 options there. So I have all these options. I have 6 different options that I could do this for. And one of them might work better. One of them might not work better. Maybe it's just, honestly, there's many different ways to go about it. Sometimes it might be helpful to think about this more geometrically in some certain ways. But sometimes there's going to be a really, really nice way, especially thinking about this first one. This first one, how do we integrate that? Do we integrate with respect to x first, y, or z? That's going to be your first thing you think about. Because which is going to think about your height here? That's what you should think about. What is going to be the easiest to think about that I have a lower bound and an upper bound of your height? Okay. Let's do a problem to kind of show you, I guess, how you might want to try to go about solving the limits of this interval. Okay. And especially thinking about the process here. It's going to be a lot easier for me to think about the process in this case too. So I have a problem here. Let me just pull it up. So the problem here states that I have, yeah, we can do this one. I have a triple integral over my region E of x minus y dv, where E is enclosed by the following surfaces. Z is equal to x squared minus 1, z is equal to 1 minus x squared, y is equal to 0, and y is equal to 2. And this is my region E. And I want to figure this out. So again, the interpretation of this is I have my region E here. We can kind of imagine this maybe as a density of some sort, and I'm trying to integrate over this volume that I'm now creating. This is a volume now because we have this dv. So what you want to try to do as best as you can, I am not an artist. I can barely draw all the limbs of a stick figure. I'm very bad at it. But what you should try to do at least is try to get some semblance of what this looks like as best as you can. Because the better you can do that, honestly, it's going to help you out so much here. So the first things I want to try to draw are these 2 parabolic cylinders. So what do these look like here? So we have x, we have y, we have z. So what I want to do is I have this x squared minus 1, z equals x squared minus 1. So if I have x squared minus 1, it's kind of going a parabolic in this way. And it's also infinite in y, right? It's kind of like a taco holder. Right? I have a infinite taco. Oh my God, that would be amazing right now, just an infinite taco. Besides the point. We have this kind of parabola here and just going off in this direction and coming back in this direction. There's no limits in y, right? So I could write this here. Maybe it's something like this, and it's going to be ending up at -1 there. So maybe like, kind of like that. And we will also go off into this direction too. I'm going to kind of wait for that 1 second. And then we also have this guy right here, which is, it just now downwards like this. Again, another infinite taco. If only we had this. And now what's going to happen is this goes infinite in this direction, right? Goes infinite in this direction here. And similarly for the blue one, going off in this direction here. Now, what's happening here too, kind of go off in this direction, is I have these 2 lines, y equals 0 and y equal to 2. I know that I'm bounded by that. Y equal to 0 is this plane right here. It's that plane, it's the xz plane. And similarly, I have another plane, y equal to 2, so let's cut it off there. So something like that. And we could think about that at this point too. I can kind of project almost I'm going to have something like this too there, where the two parabolas are going to come together. And basically what my region's kind of looking like, if you can kind of see, my region here is basically, I have these two parabolas that are kind of intersecting each other, and it's just this almost this tunnel that goes all the way to 2 here. Basically, that's the best way to kind of think about it. Okay, so I have this kind of tunnel that looks like that, and it just kind of goes in that direction, that same exact thing. Kind of that's what projected onto the XZ plane. Okay, so what I want to do instead now is to think about, okay, I have at least some visual idea of what this looks like, right? I have some visual idea. Now, what I want to do is think about which integral, which variable do I want to integrate out first, which means I need to figure out what's the easiest direction to think about what the height is here, okay? So let's think about going from each one, okay? And think about what might be difficult, what might be easiest here. Let's assume maybe I want to integrate with respect to Z first. If I want to integrate with respect to Z first here, and I'm going through this region like that, right? I'm going through this region like this here. It's kind of a weird one because I know I'm going to be bounded below. You can kind of think about, I'm always entering the region from that bottom parabola, this blue parabola. I'm always entering from that, right? And I'm always exiting from that top part. So I'm kind of thinking about this. I'm entering and exiting, right? I have this 1 minus x squared here that I'm entering from. I'm sorry, I'm entering from, my apologies, x squared minus 1. And I'm exiting from 1 minus x squared. And something like that. But then what starts to happen here is you would need to project this now. So once we integrate something out, we need to project it onto the two variables plane that we have not integrated yet. So I have integrated this with respect to Z. I now want to integrate this. I want to project the surface onto the XY plane. And if you would agree, it's going to be kind of complicated for me to see that. I think it's some form of a rectangle to kind of project it onto there. I'm not terribly sure. It's going to be kind of complicated, honestly, it will. I think it's some form of rectangle. It's not that obvious to me what it is. So with that in mind then, we might want to start to think about, okay, is there maybe another way we could integrate instead? Maybe Z is not the best way. If you might want to think about, if you want to go ahead and try to come out with that Z direction, that's cool. But it's not too obvious to me at least. Which is which here. So I'm going to erase those things. Now let's think about maybe if I integrate with respect to Y first. Let's integrate with respect to Y. Well, what does that tell me? I'm now coming through my domain in this direction here. Right? I'm coming through my domain in that direction, the positive Y direction. Where do I enter the region from? I hope you'd agree, I'm always entering, well, I see up here, I'm entering from Y equal to 0, right? I'm always entering there. Because Z, these cylinders are not dependent on Y, right? So I'm always entering from there. And I'm always exiting from this plane, this Y equal to 2 plane, which that seems extremely reasonable. So for instance, why can't I just write that Y is going between 0 and 2? That's not too bad, right? And now what's even better here, in this case, is that what we do now, since I've integrated out Y, I now project onto the XZ plane. Okay. If I project this onto the XZ plane, I actually know what they're going to look like because I have these two objects. Because what they're going to look like are just these parabolas just smushed onto that. Imagine I like kind of take this as an accordion and I like squeeze it all the way to the XZ plane. It's just going to be these two objects like that. So if I project this really quickly onto the XZ plane, onto the XZ plane here, I'm going to have two, right? I'm going to have this blue guy, and I'm going to have this red one. And this is my region now in the XZ plane. So what I've done here, I've integrated out with respect to Y. I now project it onto my other two variable plane that I haven't worried about. In this case, I'm projecting this onto the XZ plane, okay? And now what I do is I come up with just the bounds for this. I should not have any more Y's here, right? I've basically integrated out y. I'm only dealing with x and z now. And now this is actually not terrible to come up with. This is something that we've seen. This is kind of a type 1, or this is actually, this region, it seems a little bit easier to integrate vertically first, which is integrating with respect to z first here, because it kind of looks almost like a type 1 region, kind of going up in that way. So if I want to integrate this, I kind of think about this going upwards like that. I'm always entering from the blue region. I'm always exiting from the red region. The red region here is 1 minus x squared. The blue region is x squared minus 1. So I can then tell you, okay, well, I can then say that z could be bounded above and below by x squared minus 1 below the blue region and above 1 minus x squared. Something like that. And lastly here, I need to figure out what my x's are. And what I can do, if I want to figure out these intersection points here, I can actually solve for when z is equal to the same, right? This is when z is equal to 0. And so when do these two things intersect, right? These things intersect when x squared minus 1 equals 1 minus x squared, right? I could solve this out pretty quickly. I would get 2x squared is equal to 2. And then x, if I divide that over, right, I'll get that x would equal to plus or minus 1. And so therefore, with this in mind, I then have this last part will be negative 1 to x to 1. And these are my limits of integration. There are many different ways you can integrate this. Honestly, you probably could have done the same exact thing I just did initially, right? You could integrate with respect to z first, maybe project it down, and that would kind of work out that way. But here, I kind of thought it more visually. It looked a little bit easier for me, at least, to integrate this with respect to y first, because I'm given it right there. Right? I'm given it in the problem that y has to be is bounded by y equals 0 and y equals 2. So that has to be it. And so it just seems a little bit more natural to do it that way. So I'm integrating with respect to y first, then z, then x. Kind of like that. So without further ado, I'm not going to go through the whole integration here, but I'm just going to show you kind of at least where you might want to start going here, at least in this case. So what this will become then, be setting this up. The first thing I integrate is 0 to 2 for y. Second thing I integrate is x squared minus 1 to 1 minus x squared. Oops, sorry. And lastly here, the last thing I do is negative 1 to 1. And this is still x minus y, dy, dz, dx. I'm integrating with respect to y, then z, then x here. That's kind of how I go about this. And from here, what I could do, right, I could start integrating this out. If I integrate this with respect to y first, I'm going to be leaving this guy. Again, this works exactly the same exact way as double integration. You know, you let x be a constant here and z be constant. You integrate with respect to y. This becomes then xy minus y squared over 2. Between y equal to 0 and y equal to 2 here, dz dx, negative 1 to 1, x squared minus 1 to 1 minus x squared. This guy then becomes the 2 is the only one that really matters. The 0 will go away. So this becomes 2x minus 2 dz dx. And from here, we can integrate this pretty nicely. You know, we can keep going from that. But the goal here was just to kind of show you that, you know, you can integrate this in really as similarly as possible. Right now, I'm down to a double integral again. I let z be a constant. There's no z's here, right? So it just becomes pretty natural after that. That's kind of how we do it. Okay, so kind of think about hearkening back to what the problem is actually saying, right? We wanted to come up with our limits of integration. To come up with our limits of integration, we want to think about the height first. What's the easiest thing to think about the height, right? What's easiest to integrate out first? And more importantly, what might be a little bit easier to write out with the projection, right? What's easiest to project on? What shape do I know? Okay, what shape do I know? What shape can I do? Because at that point, once I've integrated out with respect to y, this is again just 15.1, 15.3, right? We can use a lot of different techniques here. Maybe this is a circle. Maybe this is not a circle. Maybe it's something else. I mean, maybe write this in polar, something like that too. Okay, So let's come up with a different problem here. I'm going to do two more problems here. This one problem I'm going to do is hopefully going to, encapsulate a couple different things here. And what I'm going to tackle now is again trying to find the volume of an object here. Okay. So this problem is going to say the following. So I want to find the volume of the solid enclosed by the following things. The paraboloids x equals y squared plus z squared, and y is equal to 8 minus x squared minus z squared. What is the volume enclosed by those? Okay, first things first. How do I compute the volume? How do I compute the volume? Well, I want you to think about this. If I have a 1, if I tell you that this integral of f of x, y, z dv here, if I give you that f of x, y of z, x, y, z is just equal to 1 the entire time, it's the same density everywhere. Same density everywhere. This will just become then just a 1 dv. Now, in our last example, what did we say that this was? Right? If I just had a double integral with respect to dA here, with a 1 there, we thought that that was the area of A, area of D, sorry, the area of D. In this case, it's just the volume of E. Basically saying, if I have all the densities the same, it's the same thing. It's just, I let that be E, and that's it. It's just the volume of E. So if I ever want to calculate the volume of a solid, I let 1, it has to be in the integrand. That's always what it is. There's no function value, it's just a 1. Okay. Now, we want to try to draw this as best as possible, right? This part here. Let's kind of try to draw this. So this paraboloid is infinite in y. It's going to be going in the y direction, and it's starting, if I plug in 0 and 0 here, it's going to start at y equals 0, right? So x, y, and z here. We start at 0, and we kind of go off in this direction here. And it's this paraboloid, right? This is in the positive x direction, positive y direction, and it gets bigger and bigger and bigger as we go forward. Okay, the next thing here is to think about this 8 minus x squared minus z squared. This again, since they have a minus sign and a minus sign here, it's going to be going in the negative x direction, a negative y direction here. And it's going to be starting at 8 at the y coordinate. So if I draw this out, this is going to be at 8 here, let's say. I'm now going to draw this going this way. And again, I have these kind of big things like that. And so what we can see here is the volume enclosed by this. It's really kind of like this football thing. It's these two kind of parabolas kind of coming together. We kind of get this kind of shape like this. It almost, they intersect at that point. And we kind of get this shape here. Okay, so a lot of things to consider here. A lot of things to consider. The first thing is, which integral is it going to be best to integrate out first? Well, it's probably not too good to do z first. And why is that? Well, if I'm over here and I integrate with respect to z first, right, I'm going to have a lower limit and an upper limit that are on the same exact function. We know that that's an issue, right? We saw that back in 15.2 and 15.3. That's a very bad issue. And similarly over here, it's going to be the same thing. If I do this with respect to x, I'm going to have the same issue, right? Coming through this direction. If I come through this direction here, kind of like going this direction, I again get, right, in the positive x direction, I'm again going to be intersecting both when I enter and exit the region from the same exact functions. And it changes as I move throughout that too. So that's probably not the best thing to do. So we might want to just do with respect to y, right? If I do this with respect to y, I'm going through the region like this. Going through the region like this. Now, if I go through the region like this, would you agree then I'm always entering the region from this paraboloid, the paraboloid y equals x squared plus z squared, right? I'm entering from there, and I'm exiting from the green paraboloid. I'm exiting from the 8 minus x squared minus z squared. And because of that, I know that y then can be bounded below by x squared plus z squared, and bounded above by 8x squared minus y, 8x squared minus z squared. My apologies. It's bounded below by that guy, because I'm going through my region. It's bounded above by 8 minus x squared minus z squared. Okay, so we've now integrated this out. Now, again, what's the technique? I integrate with respect to x. I now need to project onto the plane of the other two variables. I want to get rid of y, basically. And so what I do is I project that surface, this entire surface, onto the xy plane. XZ plane, my apologies, onto the XZ plane. Now, what is that going to look like, right? Imagine if you're standing at 8 here. Imagine you're standing over here, and you just look at this direction. What is it going to look like? Well, I hope you'd agree, it's going to look like a circle. Now, why is that? Well, do you agree the biggest thing here is this red object right here, right? It's this disk that's really going to get projected onto here, right? That's what it's going to be going forward. If I look at it, that's the biggest thing possible, right? That is honestly the biggest object that I can look at when looking at it from the x and looking at it from the y direction, and that is what gets projected onto it. You take the biggest thing possible. You take all of it as possible. Okay. So if this happens now what does that look like? Well, it's something like this. Right? It's something like that. It's some disk, but what's the radius of it? It's not really obvious. But how can we figure this out? Well, what even is this curve, right? I don't even know what this curve is. What we can do instead is take a look at seeing that this is actually the intersection between this paraboloid and this paraboloid. And so what we can do is we can actually equate these two and solve for that equation. So let's do that. So here, what we do is I say x squared plus z squared is equal to 8 minus x squared minus z squared. And now I'm just trying to solve for the intersection, which is this equation. Move over the x squareds and the z squared. I get 2x squared plus 2z squared is equal to 8. And then divide out by 2, which gets me x squared plus z squared is equal to 4. And so what does this mean? This means that this circle right here is a radius of 2. And there you go. And now we have techniques that we have. We have techniques now to be able to, use how do we write the equations for just circles, right? How do we write regions of integration? Well, it's the entire circle. I can possibly use polar coordinates now. I can use polar coordinates to go there. Now, here's the thing that you have to be kind of careful of. We can't do this all in one fell swoop. We have to do this individually. I have to integrate out y and then kind of shift variables over. So let me kind of write this down. I'm going to name this my region. I'm going to name this region D here. Okay. And again, we are saying here that my integral, I'm going to use black here just so I can write this. The integral over my region E, this is going to be the volume of E, right? The volume of E here is now going to be equal to the double integral over my region D. But I'm going to first integrate x squared plus z squared to 8 minus x squared minus z squared, my y integral here. This is still a 1 dy, and this is now a dA. Now, why am I writing it like this? You might say to yourself, hey, Nick, why do I have to do this instead? Why can't I just, go ahead and write this polar and then go here? That is kind of also part of section 15.7 in terms of cylindrical coordinates, but this actually is not even cylindrical coordinates, because cylindrical coordinates actually makes z be my z equal to z, and x and y then get changed to polar. So here what I have to do, if I want to go to polar coordinates, which I do want to, I need to first off integrate out once, because polar coordinates are only 2 dimensions. So what I'm going to do is I'm going to integrate this out y, and then from there, I'm going to then integrate this with respect to r and theta, my polar coordinates for this circle. So I'm going to go do this a full steam ahead. So if you notice, if this is just a 1 here, it just actually comes out to be, this top part minus this bottom part. minus x squared plus c squared dA. And more formally, I can write this as 8 minus 2 times x squared plus z squared dA. Okay, so now I have this. Right, if it's just a 1 here, right, it's just a subtraction of these two. Now, you might say to yourself here, and I know this sounds silly, but take a look here. Doesn't this look very similar to maybe something you did back in double integrals, right? I had a height. This could be thought of as a height, right? My highest value subtracted from my smallest value to get that integrand. So this problem can be solved either way, with a double integral or a triple integral, whichever one you want. This is really nice. There's a lot of nice similarities between them. So now what I'm going to do is I'm going to come back here, and now I'm going to think about everything. I now know that x squared plus z squared here, x squared plus z squared is going to be equal to r squared. This here needs to get shifted that way, right? Because I'm in the xz plane, so x squared plus z squared is equal to r squared. This radius here, this is a radius of 2, so the radii here, the limits are going to be from 0 to 2. And theta, because I have my full sweep, is from 0 to 2 pi. And so therefore, this integral now becomes then the integral from 0 to 2, the integral from 0 to 2 pi. I'm now going to replace where I see this x squared plus z squared, I'm going to replace it with r squared. If you just had x and z, for instance, x, because it's on your x coordinate, would be r cosine theta, your z would be r sine of theta, right, in that case. Here, you would 8 minus 2r squared. But then I have to be careful, right? Instead of writing dr d theta, I must write this r in front of it. Right? That r in front of it is very important because I need to make sure that I'm keeping the area constant, right? With the correct dimensions. So now what I could do here to solve this out, well, there's no theta dependence. So again, I can utilize the separability condition here and separate them out individually. I would have then 0 to 2 pi d theta. And then here would be 0 to 2. Factoring through would be 8r minus 2r to the third dr. This would just become 2 pi. This one here would become 4r squared minus 1/2 r to the fourth between r equals 0 and r equals 2. R equals 0 is not going to matter, right, because 0 and 0 go away. If I plug in the 2 here, this becomes 2 pi. I would get 16 minus 8, kind of doing that out, which is equal to then 16 pi. And so therefore, this means that the volume of this object here is 16 pi. And we did this in a very interesting way, right? What we said is, okay, I know the volume of E is equal to 1 dV, right? This 1 here. So now to figure out the limits of integration, I saw that it's very, very easy. It's a little bit easier than most to integrate out y first. And then what I did is I projected the surface onto the xz plane to integrate after I integrated out with respect to y. To do this, I would then define what this object is. I set the intersection, because it's actually the intersection, the biggest object is the intersection. And then do that, I get x squared plus z squared equals to 4. I now know that's a circle of radius 2. I know that I can now solve this. After I've integrated out with y, I can solve this now with respect to my polar coordinate system, just being very constant. That's at least the way you can do it. And these kind of, hopefully these ideas start to come into play a little bit more as we get more forward here. Okay. And the last thing I want to do is a problem that I've seen many students have trouble with in the past. It's coming up with all the different types of integrals. Right? How do I come up with all the different types of integrals that I have? You have dx, dy, dz. How do I flip everything too? So for instance here, let's tackle this one. I have this integral here. That's 0 to y to 1, 0 to 1, of f of x, y, z, dz, dx, dy. And what I want to do is start to think about, how do I convert this to different integrals? I want to write 6 different integrals. Right? I can write this in many different ways. And the goal here is going to start to think about projections. Projections are your friend, amazing friend. It's an amazing friend of yours. Okay? So let's kind of talk about this. This tells me a couple of things. I want to try to draw this as best as I can, right? I want to, again, try to draw this as best as I can. It's going to be pretty tough. Three-dimensional drawings are tough, but hopefully we can come up with something. Here, z here is between 0 and y. That's what it says. I'm integrating out z first. I say 0 is between 0 and y. I then tell you that x here is between y and 1. And lastly here, I tell you that y is between 0 and 1. This is my integral. Right, this is my limits. So what does this look like? Well, the first thing is, here it tells me I've integrated out with respect to z, right? And now what I want to do instead is I can flip these to go from dy dx, but I project it, and this is my object, right? This is my projection onto the xy plane. That's what this tells me. So if I project this onto the xy plane, what I can say is, okay, x is equal to y. I can draw this out. X is equal to y here is this line. I then have x equal to 1. And I have y between 0 and 1. And right, I have this line here and this line here. And you might say to yourself, okay, which one is it? Well, I have two triangles here. Which one is it? Well, as a reminder, if I go in the x direction, this is saying I need to hit x equal to y first, and then leave from x equal to 1. So it must be this region right here. That's my region. So I've integrated out with respect to z. The projection of this surface onto this is this point right here. Okay, now I can flip this immediately to go from dy dx. Why? Because this right now is written as a type 2 region here. It's integrating with respect to x and then y. Let's integrate this with respect to x and then y with respect to x here, which I can do that pretty nicely. I'm drawing arrows going up the region now. The first thing I hit here, always, I was on the eraser, that's never a good thing. With respect to y, if I go through this region, the first thing I hit always is y equal to 0. And then I exit the region always from the line y equal to x. And I know that x also is between 0 and 1. Okay, so another way I could write this could be, if I wanted to, I could say, okay, well, this could be written as, you know, I'm again integrating with respect to z first, but then I'm going to integrate with respect to y. So I'll go from 0 to x and 0 to 1. F dz dy dx. Okay. So now that was the easy one, right? That was the easiest one because I already knew what that was. So let's kind of go to more difficult ones. How do I draw this whole entire thing just in general? Well, we can kind of think about this here. If I want to draw this entire thing, if possible, which it actually is possible here, I want to think about this. I know the projection of this surface onto the xy plane has to look like this. Has to. So let's draw that. Honestly, let's draw that. I have this xy plane. I could kind of think about this as here, xy. It should kind of be down here. Right? That's my region. This is the exact same region. Right? Now, I have a couple of other things that are pretty interesting too. I have here that this is now bounded by z to be 0, which is the xy plane. I'm going up now into my region, and then I leave from z is equal to y. Okay, well, what does z equal to y look like? Well, z equal to y is just the line, it's just the plane that kind of goes up in this direction, right? And then cuts across because it's infinite in x, right? So maybe it starts up off at this point here. We can see it kind of cuts down, in this case, like that, and cuts down like this. Kind of slices across. And so what this actually starts to look like is it looks like this pyramid, in a way. It's kind of cutting up. It's kind of a slanted pyramid. And it's kind of cutting up like that. Okay? That's what it kind of looks like. Now, how do I start to come up with some of these things, right? How do I start to come up with some different regions of integration. I want to now integrate, maybe let's go with respect to y first. Okay, if I want to integrate this with respect to y first, well, what's kind of nice, and I'll tell you something really interesting, is that if I integrate with respect to y, I want to come through the region in this direction here. I'm coming through the region in this direction. Now, what's pretty interesting, if I come through here, right, I am entering the region where? Right, where am I entering the region from? Well, you can kind of see that I'm always entering the region here, specifically, from this kind of axis here, right? I'm integrating first at this point. It's kind of slicing through here. So I'm always entering the region from that plane that I'm slicing from, which is the z equals y, right? Which is z equal to y, it's that plane. I'm always entering from there if I go in this direction, right? If I go in this direction, I'm always entering from that point. So I'm always entering from z equal to y, and then I'm exiting from this guy right here. I'm exiting from the y equal to x line, which is just a plane that goes up too. So I'm exiting from x. So y is between z and x. We like that. So I enter the region from y equals z, and I exit the region from y equal to x. And then what I do is I project this surface onto the xy plane, xz plane, because I've integrated out already. So now, if I project this surface onto the xz plane, I hope you'd agree then, well, it's just another triangle. And it's actually the same exact type of triangle here. Now, how could you have seen that, by the way, right? How could you know that if you just looked at these? It's tough to kind of see from here, you know, what that projection is going to look like. But you can kind of think about this in some way, right? It intersects at the line z equal to x, right? When are these two equal? It intersects at z equals x. So it has to be intersecting at that line. Right? These two things are combining at z equal to x. So it projects onto there in that exact same way. So this is now my region in the z equals x domain, and this can be written in two different ways, right? Because again, this can be written in terms of x first and then z, or with respect to z first and then x. So let's do that both. If I write this with respect to x first here, I integrate this with respect to x. I'm coming through, it hits z, right? It hits z, and then ends at x equal to 1. And then what I do is my z components, again, are between 0 and 1 here, because I know that the highest point this can be is 1. And the reason why I know that is that this plane is z equal to, you know, 1. I mean, this plane is z equal to y, right? And I know this top point has to be, this point right here is y equal to 1, so this has to be z equal to 1. And so I know z then runs from 0 to 1. Another way I could write this as well could be going in this direction first. I could tell you that z then enters the region. We enter the region from 0, and we exit the region from x, z equal to x, right? And similarly here, my x then would be between 0 and 1. And so using this and this, there are two different types of integrals I can write then. I can do dy, dx, dz, or dy, dz, dx. And lastly here, to kind of close everything up, let's integrate with respect to x first. If I integrate with respect to x first, this might be a little bit tougher to think about, but where am I integrating with respect to x? So if I integrate with respect to x, coming back down to my, I'm going to draw this as a red line through here, kind of coming in this direction, right? If I come through this direction, where am I always entering from? I'm always entering from that x equal to y line, right? That plane that kind of shoots up, right? I'm always entering from there, okay? So that means that if I want to integrate with respect to x first, I always enter from the y, x equal to y line, right? I always enter from that plane. And I exit actually, from when x is equal to 1, I always exit from that line. And that plane that kind of just shoots up. So x is between 0 and 1 here. Now, the last thing I need to do is project this surface onto the xz and onto the yz plane. And on the yz plane, again, this line is y equal to z, and I know it's going to look some shading like that. So again, I again have here x to z, I have y and z here, and it's this plane again, this exact shape again. And what we can do again here is we can make this either type 1 or type 2. We could go, for instance, and say, let's integrate with respect to y first. I go across here. First, I hit z, and then I hit 1. And then lastly, for z here, I go from 0 to 1 again. And more specifically here, I could then go z first. I would start at 0, then go to y. And then y here, I'll go from 0 to 1. And now here are your 6 regions of integration. Right? These are the 6 different ways you can write this. dz dx dy, dz dy dx, dy dx dz, dy dz dx, dx dy dz, dx dz dy. And you do this via these kinds of ways. So at least trying to draw the picture as best as you can give you some insight. It is pretty difficult to do some of these problems without drawing the picture out, or if you're not given the picture, it's pretty difficult. But a lot of these things come from intersections, right? The reason why we were able to say, you know, why does this shape on the xz plane look like that is where does y and intersect here? It's z and x, right? So it intersects at the line z equal to x, and that's why it comes into this point, and so on. So yeah, that's kind of basically it, how you were going to go about this. It really will depend wholly on what the function is, which one you should pick, but there's really not a bad option here, at least at the moment. Maybe the function, you know, maybe looks a little bit better if I integrate with respect to x first. Lets me kind of integrate something with respect to z or something like that then later. Kind of have to take that as a you know, a problem dependent wholly on z. So that's it. So at least for this video. So what did we kind of do, just kind of looking back? We understood that what the triple integral really means now. The triple integral over a volume E, we're over a volume now. If I have this function f of x, y, z, we can think about this as the density of the object at every single point in there. And integrating over it kind of we can think about the, you know, the total mass. If f is all positive. If it's not, we have to think about this in a different way, but for right now, you can think about it almost as a mass. What we can then think about here, we see that we have 6 different ways we can write this. And to kind of come up with your bounds, you want to try to visually see what's going to be the easiest for your height here. Where do I enter the region? Where do I exit the region from? Right? Where do I enter the volume? Where do I exit the volume? If you come up with those pretty nicely, then project it onto the other two variable planes, that hopefully helps you out a lot. And so we did some problems here, seeing that the intersection might help with the projection. And also here we saw, you know, being able to come up with a full, you know, full 6 different variable ways of writing out, you know, the integrals here. Kind of doing that exact thing, the projections and coming into type 1 and type 2 there. Okay, so I think that's basically it here for this video. So yeah, let me know if you have any questions about this. Yeah, I hope you guys are doing well. And yeah, keep enjoying everything. And I hope this makes more sense. I'll be doing some more videos on 15.7, 15.8 coming up for cylindrical and spherical coordinates. But let me know if you want me to do any other videos. I'll be happy to do it. Stay safe, everybody.